Okay, let's start. So, firstly, just a bit of logistics. Tomorrow is officially a holiday, but I'll still do my office hours, so you can drop by, as in it's on Zoom anyway. So, just want to mention that. Secondly, Swapnil's lecture and my lecture kind of got a little bit out of sync, so there's some stuff which I'd hoped to cover, but I guess he expected I covered. So I realized that some aspects of his lecture may not have been entirely clear, but hopefully the material I'll cover today will clarify that. So some of the jargon related to neural networks. So apologies for that lack of coordination, but I was just going slower in the lectures, unfortunately. So this had to do with when he was talking about different kinds of layers and stuff like that and all. So after I'm done with this retrospectively, some of that material would be clear. So where I was before last week, Thursday, we were going through kind of different kind of machine learning models, and I talked about just early stages of neural network, that how they historically evolved, and kind of the early neural networks were basically, well, the really early neural networks. I mean, if you recall this picture I have kind of started in 1940s or so, they actually were not even unidirectional neural networks, okay, as in information flowing from left to right. They had all sort of like information flowing forward, backward, different type of learning algorithms and all. But then in around 1960, this concept of perceptron emerged, or multi-layer perceptron. So basically they looked like this: multiple layers of fully connected neural networks, and where, as we had discussed kind of a little bit earlier on, each neuron basically takes a linear sum of inputs from all neurons from the previous layer and then subjects it to a nonlinearity and adds a bias to it. So that's why we have kind of this one term, and essentially for each neuron then you have as many parameters as the number of predecessors it has, plus one more for the bias factor. And so given this kind of structure, you can see lots of things. How many layers, how many neurons? You can think of that as parameters of the architecture. So when Swapnil talked about neural architecture search, so at some level you can say, look, if I decided that I'm going to use this type of architecture, then the parameters are going to be how many layers and how many neurons in each layer. And then and then the only thing that is fixed in this thing is input layer, because input layer will have as many neurons as the number of features you have, and it may also be features, may also be pixels in an image, samples in a window of, let's say, sound, but it could also be some statistical features that we compute over a window. How many hidden layers and what the number of neurons in each one of those hidden layers is kind of up in the air, right? I mean, of course, you pay more in computation, but presumably also more in expressivity. There is a theorem of sorts, or whatever, there's a result of sorts, which basically says that if I have a two-layer network, as in something with one hidden layer, and if that one hidden layer is infinitely wide, then I can express any computation as I can. Not a very useful result, but it kind of begins to say that big networks can express any computation that can be expressed. They can express an arbitrary mathematical function, or those of you who know about this, like it's equivalent to a Turing machine. So it can, anything which is computable can be expressed. So very loosely speaking, you can say that a large enough network can learn any function, can express any function, and then given a proper training procedure, hopefully you can find the parameters which will correspond to the particular function you are trying to learn. And the other comment is that the real life neurons in our brain and actually you also have neurons elsewhere. There are neurons along our spinal cord also, for example, and I think there's some particular part of our some other organ where also there are some neurons present, but Point being that they communicate, as I mentioned earlier on, not using voltage levels and all, or not even, they communicate using spikes, and the rate of the spike, how many spikes per second, expresses the value that is being expressed. And then basically the structure, so they communicate across essentially what you can think of as a wire carrying the signal, and then neuron, very loosely speaking, acts like the following. It sums things coming from the preceding neurons, applies some nonlinearity, and then generates the output spike train. So that is what had motivated kind of this first order model of neurons, and the different versions basically differ in what nonlinearity that you choose to pick. And as I mentioned again in one of this slide is a repeat of that. Usually, if it was linear, it doesn't give you anything, because linear functions of linear function is another big linear function. So these neurons are designed so that they saturate, but these kind of functions are tanh and sigmoid. They are hard to compute, require floating point arithmetic. Again, Swapnil kind of made a point, floating point arithmetic is hard to do, and also it's very hard to do in analog circuits if you were doing. So usually we go for some simpler forms of nonlinearities to make these things work out. So our problem then reduces to find an architecture and find parameters for that architecture. A simpler version of the problem is somehow you have said, look, my architecture is fixed. By that I mean how many layers, how many neurons in each layer. That's fixed. And then our problem reduces to just finding the parameters for every neuron in every layer that we have. And very, very loosely speaking, the optimization strategy that's commonly used is what is called a stochastic gradient descent. Essentially, wherever is a starting point, you kind of follow the you start with some values for those parameters. Usually you initialize them randomly, and then you always perturb them in the direction which will minimize the error relative to what you are seeing with your current model. So currently you have some values of parameters, and then you see how should I perturb them. So essentially you are seeking the derivative of the loss, the derivative of the error relative to the parameters, and then you are going to find which direction should I perturb take a step basically. So find the downhill side and go there. The stochastic part refers to the following. You have a training data set, right? So we don't know the mathematical form of the function, so we can't compute the true derivative. So what we do is we are estimating the derivative. And if I have a training data set, I'm going to estimate, the best you can do is to compute for every point in your training data set, find the slope, and then perhaps take the average slope. But that means at every time I have to compute the derivative, I have to take the whole data set. So that's very time consuming. So we take small samples, or what's called as batches, out of that data set. So the word stochastic comes from the fact that we are not doing the true gradient descent, we are doing an estimate on it. But at a high level, the story is very simple. Compute the derivative and take a step in the direction where the derivative is the steepest. So the whole thing then boils down to is that given a neural network, I have to find the derivative of the error with respect to the parameter vector theta, or alternatively with respect to every parameter, and then once I have done that, then I can do the gradient descent. The error could depend upon what you are doing. So usually if you are using the neural network to estimate a real value, then it's very common to use a least square error, want to minimize that. But if you are doing a classification, then there are other ways that you can look at the error. So fundamentally, at any moment in time, you have a current theta vector. You see what your model predicts with that current value of theta. you compare it against what the true value is, that's the t. So you look at, and then across all the data points that you have, right? So n represents how many data points I have. So across all the data points, I compute overall error. So in this particular case, we are doing a summation of the square of the error at every data point, and then our goal is to compute how this error function changes with respect to our parameter vector. This part is what we need to compute, and it can be done analytically if your neural network, the nonlinearity, is differentiable, right? Because everything else plus multiplication is differentiable, so this thing just looks like a gigantic sort of multi-layer linear function, but with some nonlinearity thrown in. So if you take Professor Jonathan Kau's course, for example, they kind of show you how, for a network like this, which we had, how you can compute this, okay? And it's a laborious calculus exercise in calculus, but the couple of big things that happened in the history of this thing. One is sort of people developed this thing called back propagation. So kind of our goal is I have a multi-layer network, the output somewhere out here, right, and I'm computing the error, but then I need to find the derivative of that error with respect to, let's say, a parameter which is sitting deep behind. And this is where chain rule from differential calculus comes into play. So basically, I first find the derivative of the output with respect to the last layer, and then I propagate it backwards. So that is what was called as the back propagation algorithm, and came about in late 70s or so. And then sometimes in 90s, software emerged where basically all I have to do in software level is describe the how many neurons, describe the connectivity, and then the software can take care of all the differentiation. So this software, this thing is called AutoGrad, automatic gradient, and that simplified things considerably. So today you could basically go to a tool like TensorFlow or PyTorch and then just define your network, including the nonlinearity you have, and it can take care of computing, and you describe your error function, and then it can take care of the derivatives for you. And there are standard error functions which people commonly use, so that's how kind of things work out. So the way the whole process works is that at some let's see, so at some point you will have which slide do I want to use? Let me stick out here. So at some point I will have some value x, and what we'll do is I'll do a forward pass. So I'll given that x, so this is from my training data, right? So I have an image, and let's say something about it, like what object type it is. So I'll take that image, I'll propagate it forward. So I'll go take a forward pass. So I'll compute each value, all values. Ultimately, I get an output. Then I compute the error, and then I take a backward pass during which I compute all the derivatives. So I first compute the derivative of E with respect to parameters in the last layer. Then I take those values and compute it with respect to the preceding layer, and so on and so forth. So that's basically what the training algorithm looks like. We do a forward path, we calculate the derivative of error at the output layer, and then we go backward, where for each one of the from last onto the input, we compute the derivatives with respect to all the weights, all the parameters that we have, and then eventually we have to figure out how to adjust the weights, right? So once I have error derivative of error with respect to all the parameters, then I have to adjust you can think of all the parameters lined up in a vector. I have to figure out how to adjust it, and that part is relatively simple. We'll say new theta, the new parameter vector, is the old parameter vector minus the something which kind of is which takes into account how error is sensitive to each one of the parameters. Essentially, it is at this point we are going to do a gradient. We are going to find which is the steepest direction to go after. So loosely speaking, if you are this is mimicking this notion that if I am in some sort of a terrain, and if I want to reach the bottom, then I'll always try to go down. Actually, if you recall, in one of the earlier lectures when I was talking about scheduling of operations on multiple processors, we had, if you recall, we had this algorithm called simulated annealing, where we were again sort of thinking of our optimization function as an energy function and then going down there. And in simulated annealing, kind of the main part was always going down is bad, so occasionally we would go back up. Here we always go down in the way it is shown out here, and it turns out it works pretty well, although there are variants of this training algorithm where there is also the possibility of occasionally going up. So a lot of research has gone into this step, where currently what I have shown is we basically always attempt to follow the steepest gradient, but people kind of modify this thing in order to achieve better results. So that's the basic idea in deep neural network. At its core, super simple, but there are all these things. There are different training approaches different approaches at this step, different error functions, and different non-linearities. Those are the things people play with, but otherwise at a high level, they're all the same, and these are all automated for you. So you could literally just go in and define your network architecture and then throw data set at it, and it can train it for you. What Swapnil also described was this additional step, that beyond training, we also want to find out how many layers, how many neurons. That's the architecture part, and that is what the newer tools, which are the NAS tools, do. They not only so they don't simply, given a network architecture, train it, but rather they also try to find a good network architecture, and this is where TinyML and such tools, they try to take into account that if you have too big a network, then problems may happen, like it may be too slow to run on your platform, it may be too big to run on your platform, the network may be too huge that it may just be memorizing everything. So I give it, you can just think of it this way, that if my network has too many parameters, then given a data set, all it has to do is, for every point in the data set, it can just memorize the value. It can act as a big read-only memory. Why is that bad? So let's say my training procedure takes I have a big neural network, I have some amount of training data, and my training procedure, what it does is, it finds parameters such that if I give training data number 1, it has memorized precisely the output value. I give it training data number 2, it has memorized the precise value. It's just it just created a lookup table. Okay, so that's, let's say that's what we do. Why do you think is there something wrong with it, right? I mean, so I precisely remember for every value in my training data what the corresponding output value is. If I create a system like that, is there something bad about it? Yeah.
You won't be able to abstract.
Yeah, it won't be able to abstract that. It won't be able to generalize. Okay, so kind of the idea is, it's kind of like if I give my training data may be noisy, right? I mean, it may have, imagine the following, right? I mean, I give you a set of points which lie on a straight line, ideally, but when I make the measurement, they are noisy. So I kind of get points which are crooked points, but are around a line. We do the best fit line for doing that, right? So the best fit line relies on the observation that those points we know are being generated by a linear process. But if I were to just use a high order polynomial and just fit according to the the points which are lying kind of more noisily, then I will have a bad system which is overfitting. So that's the term. So you don't want overfitting. So whenever we are doing this, This is called the bias variance trade-off in training, not just neural network, any model, that you want a good balance between being accurate on what the training data you have, but also between the unseen stuff, right? Stuff which is still in your training domain, but is able to generalize. So if I give it, if I give to it an input which is somewhat different, I would like to expect reasonable results out of it. So so when we are doing NAS, you probably don't want too big a model. For that reason also, big models have a propensity to perhaps remember. So other things. Swapnil had described that how we can shrink the model by discarding neurons, discarding weights which are close to 0, for example. I can make the model smaller by also having fewer bits representing the values, those kind of things. But there are some other things also where we bring to bear additional knowledge about the type of what we are operating on, images or sound data or sensor data or whatnot. So in particular, there are two properties that are exploited, and a lot of this work happened in computer vision, so they come from there, but it's equally valid for other sensor data also. So one is structural locality, and that refers to the fact that the output at a point depends upon inputs nearby in time, nearby in space. So for example, let's say I'm looking at an image and there's a clock on the wall. The fact that it's a clock, that decision depends upon pixels which are near there and not some far away pixel. Okay, I mean, in general, that's a reasonable thing to state. So what is happening in a scene or a waveform at any given point in time or space kind of depends upon values nearby. So that's the locality part, that an output neuron depends upon input neurons. If I were to think of neurons lying in a space, let's say, right, so vision problems, so we think of like when we start out, each neuron picks up input from a pixel. Okay, so you can already assign location to those neurons. If it's a time series, I give you a bunch of samples in a window, I can assign neurons for different time steps. So I can talk about neurons being at a particular point in space or time. This is getting annoying. What this is basically saying is that a decision at a particular point in image or a particular point in time series is going to depend upon the neuron in the previous layer on neurons which are at that location or at that point in time. So in an image, a neuron would more likely depend upon nearby neurons in the preceding layers as opposed to faraway neurons. And the second one is translational equivariance. And what it says is, if I, again, going back to my example, so I had an image with the clock at some location. Let's say I shift my camera, the whole image shifts. Then my decision about what object is at what location will shift accordingly. So I'll state the clock. If the whole image was shifted by 1 meter, then the clock location will also shift by 1 meter, right? So there is a expectation that as the signal shifts, then the corresponding predictions from it would also shift. It's closely related to most of you are electrical engineers, so when we learn about signal processing, so we talk about linear time invariant systems, right? So the time invariance part is we shift the signal and kind of the output will shift accordingly, right? I mean, equivariance is closely related to that. So it's basically relying on translational invariance, translation in space or time, which exist. So that led to the idea that instead of fully connected layers, we can get away with what is referred to as convolutional layers. So instead of a neuron in one layer getting input from all the neurons in the preceding layer, the locality says that a neuron in a layer should perhaps only get input from, let's say, neurons within a certain distance in the preceding layer. Okay, so that's one part. So in terms of our going back to a figure like this, it might say that a neuron out here will only get, let's say, neurons from 4 neurons immediately underneath it. So that's the locality part. Equivariance says that a neuron looks like a neighboring neuron and it looks like another neighboring neuron, right? I mean, as I shift, nothing should change. So in other words, going back to this figure again, if I look at, let's say, this neuron, and let's say look at the neuron which is under it a little bit upwards, so this neuron, look at this, right? It will have some weight. And because there's equivalence, it's saying that this neuron connecting to this will have the same weight, or this neuron connecting to this will have the same weight. Okay, so it's basically, connect like this to this. So it's basically saying that if I look at a neuron at a particular layer and look at the various weights it has to the preceding layer, equivariance says that each one of these neurons should look the same. In other words, they share the weights. So that if let's say my input image were to shift, then all that will happen is that previously whatever was the value at, let's say, this neuron, if I shift the whole image by 1 pixel, then with the shifted image, the neighboring neuron will get that value. Okay, so that's the equivariance concept, and they both relate to kind of a real life thing, right? I mean, structural locality is very reasonable, right? Our world is not random. I mean, it is actually referred to as first law of geography. That in geography, there's also something called Kriging relationship. But basically, it says that nearby things affect us more than far away things. Okay, and right, diffusion processes are like that, right? I mean, if you let's say there is a source of radiation out here, then the radiation field will decay, right? I mean, so generally in sort of physical phenomenon, this is a reasonable thing to say that there's some sort of a locality that exists. And the other thing is, world is well behaved, so as we shift, the whole thing shifts accordingly. So what we are bringing to bear out here is some prior knowledge about the world. This is what we would call as a structural prior. Effect for us is that it helps reduce the parameters, right? I don't need to have a neuron connected to all the neurons in the preceding layer. And secondly, a neuron in layer and a neighboring neuron in the same layer, and they share the same set of parameters with respect to the preceding layer. So I can make use of both these facts to make for a much more compact footprint, fewer parameters out here. So another way of thinking about it is therefore that let's say I had an image, right? I mean, so instead of so let's say my image was 32 by 32, and let's say it was an RGB image, so it had 3 values per. So one way I can think of this image is as if it's 32 by 32 times 3, that many values. So I can think of the whole thing as a vector. But once I think of it like this as a vector, I have lost all sort of the structural intuition, right? I mean, to me, it's just a bunch of 3072 numbers. And in this particular case, I would think of it as that I would need that many weights. So let's say, for example, if I had 10 weights per this, I'll have a total number of weights like this. But the moment I start thinking of the image as an image, is 32 by 32 and it has a depth of 3, and now I start thinking of a particular pixel, I can now begin to take into account locality. I can begin to take into account that values repeat. So what we can do is we can start saying that a neuron in the next layer is really, its weights are like a little filter, 5 by 5 by 3. So it's basically saying that relative to a neuron out here, I'm only looking at a tiny window of 5 by 5, so only 25, and I'm doing so for each one of RGB, so that's the 3 for RGB, so 5 by times 5 times 3, and this is what every neuron in this layer will use. So instead of all those large number of parameters, I have a very small filter or kernel that gives me all the parameters, and then we repeat this thing, right? I mean, so going back to convolution in signal processing, that's what we are doing. So a neuron at this point essentially takes that kernel, multiplies with the corresponding neurons in the input layer, and works of that. And a neuron out here would do the same thing except for a different set of input neurons. So I have replaced all those parameters by this filter kernel. Okay, so big win, fewer parameters. It obviously complicates your computation of derivative a little bit, because the same thing is to be like I'm no longer computing derivative of error with respect to weight for a particular neuron. I have to make sure all neurons get the same kernel. So there's some slight twist that come into play, but that's what we do. So essentially in the second layer, for every neuron in the second layer, so my second layer is also shaped like an image in this case. For every place, I'm going to take this kernel and apply it to the corresponding position in the input layer, and I'll repeat that process all the time. So these are called as convolutional layers instead of fully connected layers. And big win, as I said, is far fewer parameters. So and then usually what happens is, so here you see that I had one filter, so the depth of the second layer is only 1, but instead of a single filter, I may have, let's say, k filters, in which case each filter will output a different value, and then my next layer will have a depth of k. Each activation is really a vector of size k. So intuitively you can think of it as these little things are filters which are looking out for some features, and then each bit or whatever, each value of the activation map corresponds to that. So like it could be one filter looks out for green color, another looks out for blue color, another looks out for straight lines, another looks out for whatever ellipse or something like that. So these filters look out for different features in the preceding plane and then provide a value out here. So too many parameters, convolution helps you out by tremendous reduction in number of things. Okay, so that takes care of this. Let's see. Oh yeah, another part which we okay. Yeah, the other thing I want to mention is that in a typical well, actually one thing which is not in the slide is, while I'm showing it for images, you can expect the same thing for, let's say, accelerometer signal or whatnot. The only thing is that now we are just looking at like one row of an image. It's a 1D signal. One thing to be careful, and I often see people make a mistake, is convolution relies on those two properties: structural similarity, structural locality, and translational similarity. You have to be careful that, so let's say I give you a light sensor and a sound sensor, and you have two time series emerging. So it's a sensor with two channels. There is a light channel and there is a sound channel. It's very reasonable to say that the light channel would have locality in time, the sound channel will have locality in sound in time, right? But it's not reasonable to say that sound and light are necessarily correlated at the same time. In general, they may not be. So a mistake I often see is that oftentimes if I have a multi-channel sensor, people often, what they do is they think of sensor 1 as row 1 of the image, sensor 2 as row 2 of the image, sensor 3 as row 3 of the image, and with time along, let's say, the x-axis, and the different channels arranged along the y-axis, That is not correct, because there is no reason the different sensing channels are correlated. So if you have different sensing channels, it's better to think of them as entirely separate 1D images, okay, with no correlation among them. Okay, so another thing which we can do to reduce number of parameters is to shrink the size, right? I mean, if we were to only apply convolution, then if I have an image of k by k, my next layer would again be kind of k by k, okay, plus minus 1. So this is where a concept called pooling comes into play. What pooling does is it takes my image or activation map and then looks at bigger chunks of it, like 2 by 2 chunks or 3 by 3 chunks, and then applies some sort of a statistical function over it. So for example, there's something called max pooling. So what max pooling does is, it at any given point in time, it takes your activation map, which is, think of it like an image. In this particular case, it's looking 2 by 2, and within every 2 by 2 super pixel, if you may, it takes the max value. So this guy is 1156, so you see a 6 out here, or the blue one is 1034, so you see a 4 out here. So max pool basically takes forms these super pixels by taking the max. There is similarly you can think of you can do a median or you can do a average, but max is very common, and there is again some biological justification behind it that neuroscience people talk about. So what this does is, it takes a output of convolution layer and then reduces it in size. Okay, and then how much reduction happens depends upon how much pooling you are doing. So a very common structure of neural networks then is convolutional layer followed by a pooling layer, convolution layer, pooling layer, and you kind of have a few of these alternating convolution pooling. Sometimes you skip the pooling. So very commonly, maybe 3-4 such layers in a deeper network, maybe 10 such layers happening. So that's the pooling part, and it's helping reduce and contracting the information. That's what it is doing. So when we put all of these things together, then what people often do is, they kind of studied early days of neural networks, as in the past decade, let's say 10 years ago. What they did was, they kind of studied what the different layers were learning. And the way they were doing was, they were looking at activation value for a particular neuron, and then they were trying to see when was that neuron output more positive, like giving a high value, okay, so when the neuron was more active. And what people discovered was the following. What they learned was that in these kind of architectures where we are layering things, right, and start with an image and then we go through a convolution pooling, so and so forth, early layers learn features which are very local. But then because we are doing pooling, so we are kind of creating these bigger and bigger regions. So as we go higher up, they learn features which are more complex. So for example, early layers may learn just about a patch of color or a line which is, let's say, 30 degree, 60 degree, like those kind of things. But by the time we reach deeper layers, they begin to learn entire things, like concept of a cat or a concept of an animal. So by the time we reach deeper layers, we are learning bigger features, bigger concepts, maybe wheel of a car, whatever, handle of a bike, or the fact that they have a human-like face or stuff like that. So that's what people have discovered. So you basically have low-level features in early layers, and you have high-level concepts there. And then all of this is followed by a fully connected layer. And what the fully connected layer in some senses does is a bit like a decision tree. So it may say, it's a car if it has wheels and doors and whatever, has particular shape or something like that. So the fully connected layer doesn't look for features, but it combines features, it combines concepts, whereas the convolution layers look for features at higher and higher scale, right? I mean, very local in the first layer and somewhat more global in the subsequent layers. But one thing to remember is, if in case of an image, I fed the whole image to the first layer. So you could argue that this thing is able to see and make decisions based upon the entire image. If I was taking a time series, the problem we face is that our time series is semi-infinite. So we can't just feed the entire time series into a neural network. So we have to divide it into windows. So we are going to feed a window worth of data into the first layer, and it would be just 1D version of it, and I will work off that. So anything I discover would be limited to what is in that window. So let's say I am looking for human activity, and you decided on, let's say, a window of 5 seconds. Then the activities you can detect are those which can manifest over 5 seconds. I can't detect more complicated activities which can only become clear if I have a longer time period. So unlike images with time series, the choice would matter quite a bit, how much you feed, and it also has implications on real timeliness, right? I mean, because if I make the window size too long, then I have to wait to identify the decision. So time requires a little bit more convoluted thing. Okay, let's see. Okay, so that was images. Next issue that we face is that this architecture that we have, like all this convolution and all, is entirely memoryless. It has no, in digital logic terms, it's purely a combinational logic. It just takes an input, computes an output, and you give a next input to it, it will compute the next output. It has no memory from one image to another image or one window to another window in a time series. So whereas certainly in many applications we have to deal with sequence of something. So let's say I can feed to you a GPS my GPS trace, and I may ask you some question about, let's say I feed to you my GPS trace for a year, and I ask you, where is my home? What would you do?
I guess you have time in that example.
Okay, let's say I don't have time in that. Even then you should be able to, right? I mean, it's the most frequently visited place, right? But yeah, if there's time, then place where I sleep most of the nights, for example, right? Okay, so as you can see, to do that, you need memory, right? I mean, if just from a given snippet you can't. A lot of things are like that, right? You need memory. If there's a video and I'm trying to figure out what activity, let's say it's a 30 frame per second video, and I want you to identify whenever the person in there is making a sandwich, let's say, right? Again, you'll probably have to look over a sequence of frames to be able to do that determination. So in general, we do look at tasks where I need memory. So if I have these kind of systems, right? I mean, convolutional or fully connected, any memory has to be handled outside, right? Any logic to figure out I was making a sandwich, whatnot. Maybe what you can do is every frame it gives me an independent decision, and then I can have some outside logic to figure out what was I doing. I could do that, but it would be nice if neural networks could handle sequences natively. So a couple of examples. This is, let's say, my notional example of my GPS trace. So I could take the GPS trace and plot it as an image in a latitude longitude thing, and this is for some animals, not mine, but looks okay. From this you can begin to make some inferences, and particularly if I told you where the starting point is and all, you can kind of firstly you can begin to make inferences about how much is someone moving, are there frequent patterns happening in this thing, those kind of things you can begin to tell. So one thing I can do is I can embed certain kind of traces into an image like structure. This is another example. This is I think this is what, AC Monte or something. Yeah. Mean time seems like something on the sleep pattern. The point is, I can make frequency time spectrogram, right? I can. I think Swapnil had also shown something like this, where kind of each snippet basically gives me the spectrum. Okay, so I basically short time Fourier transforms, which short time Fourier transforms, which are kind of repeating. So, and looking at things like this, you can think of it as an image, and you can begin to interpret it. You can certainly apply computer vision techniques to make some things. I mean, particularly if something has some particular pattern to it, like for example, certain devices may have certain spectral features, and then you see them appearing in time again, so you can begin to make some statements around it. So I could certainly do that. I can cheat, but so two approaches, right? So one is I can handle memory and state outside, or alternatively I can map my signal to an image and then handle it as an image, because there are a lot of image related neural networks exist there. So so I could do that. I could also, another thing I could do is I can take some window of my time series and then apply convolutional neural network over that. So for example, let's say I had a video and 30 frames per second. What I could do is, instead of operating over a single frame of image, I can line up 10 frames of images into a more gigantic image and feed that into a neural network. So that would be a window, or here I'm showing it with sort of scalar time series, right? So I can take multiple samples, concatenate them, and then feed them. So I could do that, and then again think of them as a purely combinational logic, right? But instead of one sample at a time, I take a window worth of sample and feed them in. So I could do that. So these are all approaches. But what if the neural network fundamentally had concept of time built into it? And that's what's referred to as recurrent neural networks. And kind of the idea is that, think of it like the following, that the neural network at every point in time, at every moment in time, takes the current input, produces an output, but also takes a state and produces a state. So I'm sure you all have done digital logic courses. So when we first talk about sequential logic, we talk about sequential logic or a finite state machine in terms of it has an input, it has an output, it has a next state, and it has a current state, and it feeds back through a state register, right? So our whole sequential logic looks like a combinational logic which has two inputs, current state and current input, and it has two output, current output and next state. Same thing out here. So what's happening is that at any time step, so like for example, let's say I'm looking at this guy, okay? So the green part is referring to the state. So at any point in time, it is taking an input from previous time step, forwarding some value to the next time step, taking some input currently from the outside world, and producing the output. So this is the sequential logic counterpart for neural networks, and these are called recurrent neural networks. And what would happen in this case is that you can imagine one mode of operating this thing is that I can actually, let me just step back. So our normal neural networks thus far, at any point in time, took an input, produced an output, and our next time step was totally independent. But now what is happening is, at any time step, I am not only producing an output, but I'm also forwarding a state, some sort of a memory, to the next time step, and the next time step is making use of both. So I can use it in many ways. For example, I can give it an input, and I can ask the neural network to produce a time series. So it could be, my input could be whatever, sound of a car. Okay, so I can just describe something once, and then I expect it to produce a time series. So this is some sort of a synthesis, right? I mean, one group in the class was exploring physiological signal generation. So you can imagine things like that. Generate me a time series of some form. Many to one. I can give it a time series, and I can ask it to classify it. So I can give to it a time series, and then say, tell me what type of sound it was. Big plus out here is that I am no longer limited by how long my time series is. I can give to it a time series of an arbitrary length, because what I'll do is I'll have a special symbol called start. I may have a special symbol called end. So what I'll do is I'll feed to my system start, measurement 1, measurement 2, measurement 3, measurement whatever 1001, stop. And then when it sees stop, it outputs a class label. So I could do that. I could do many to many. So where I can feed a time series and it will produce a time series. Can you think of a use for this? So black box, I feed a time series. So I basically say start, measurement 1, measurement 2, measurement 3, measurement 4, measurement whatever 1,000,010, stop. And then once I do that, it then starts spitting out a time series. And again, it does the same thing. Start of the time series, a bunch of values, stop of the time series. Can you think of an application for a system like this, which given a time series produces a time series? Someone else? Anyone? Time series input, time series output.
Caption gives it away.
Huh?
The caption gives it away.
Okay, there is something else. This is a sensor class, so not English to French. Huh? Yeah, control system, good, right? Always sensor values coming in and it's putting some action out, right? I mean, so camera coming in and steering wheel control output, for example. Okay, so but in that case, it's always happening. Here, I give the whole thing and then it's doing the whole thing. So the example of this might be some sort of filtering, for example, or I mean, you could have easily English to French. How about lip video to sound, right? I mean, that would be an example out here. Whereas the control one is really more like the final one. Okay, so recurrent neural networks are sequential counterpart of combinational logic. So you can think of RNNs.
Quick
Yeah,
question.
please go ahead.
Yeah, from the previous slide. Which system of many to many could be used for an application of, for instance, taking like a dash cam video off a car and then estimating the speed?
You tell me, someone. Which one of these would it be? Yeah, this one.
Okay.
Right? And actually, that's interesting thing to ponder about, that does the neural network learn some of these things like concept of speed and acceleration? Like, for example, let's say I show to it animals of different speed and the corresponding labels. And then I ask, so let's say I don't know, let's say I show it videos of whatever, a snail and videos of a tiger, and ask it to learn the concept of many to one, right? Whether it's a snail or a tiger. I wonder whether it will learn the shapes of things or whether it will just rely on the speed, right? I mean, we humans often rely on these other things also. There is some pretty cool work in recent times, including by Professor Achyuta Kadambi out here, exploring can these things learn or discover laws of physics. So there's some work which has shown that if you show these things, they can begin to learn like F equal to ma, or kind of the standard Newton's laws of motions and stuff like that. So there's some evidence that they pick these things up, although there is also a lot of debate around it, which is oftentimes the same physical phenomenon can be expressed in many different ways, right? I mean, at the very least, I can express something in time domain and frequency domain, for example, and somehow these papers magically always converge towards a particular representation. So leads to the question that, are we biasing them somehow? Okay, because one could have learned it a different equivalent representation. But anyway, there's some interesting work happening in that space. Learning laws of physics from these things. Yeah.
Could you show me that literature during the break?
Professor Achyuta Kadambi is a UCLA professor here.
Okay.
So you just go to his website. Yeah,
Cool.
he has a paper. Yeah. Okay. So, your question? Yeah.
So not in the previous slide, but before that. Yeah. Maybe before. I don't remember, but yeah.
Mm-hmm.
So like you said that merging pictures together like a frame of image.
That was this one. Yeah.
this one,
Uh-huh.
right? Like how does it help with the training process?
No, it's not about training. It's just about being able to get the temporal look beyond a single frame. So, right? I mean, so if I'm trying, so I can basically instead of like, was it, let's say, whatever, some sporting event, right? I mean, you're trying to classify. So, a single image may not tell you, but a sequence of image tells us. And one way to handle it without introducing RNN would be to just think of it as a gigantic image. Yeah. Yeah. By the way, just also wanted to mention, since we came back to the slide, there is a whole set of literature where people have looked at creative ways of taking time series data and mapping it into an image. Okay, so what I showed are kind of very simple type things. There are some more interesting ways of mapping into images, which kind of bring out recurrent structures in the that may exist in the time series and all. So yeah, there's literature around that also. But these were, I would say, these were all attempts to introduce time without bothering with state. Now that debate has always existed, and recurrent neural network emerged as a way to introduce time, but then the pendulum has also swung back, and I'm sure many of you have heard of terms like transformer architectures and all. They basically go back to doing everything again, just without having a concept of state, basically. Okay, so there have been sort of swings in that direction. But RNN, the concept of which is pretty old, from 1990s, essentially are doing this, right? I mean, they're taking X, they're producing Y, but there is some internal memory. Okay. By the way, there's some interesting history around this also, because one of the running feud in neural networks is that there is a group in Switzerland which did a lot of work along these things, but then, let's say 10 years ago or so, some of the work out of Facebook, Google, Stanford happened in this, and they refused to acknowledge the existence of that work. So that led to a lot of bad blood and kind of finger pointing and stuff like that. I think historically these things did emerge in 1990s, but perhaps maybe they were ahead of their time, perhaps they were the theoretical concepts were put forward, but they were not applied in practice to the extent. So whereas once big companies entered into the fray, they got applied. So there's a lot of kind of interesting bad blood behind it. But for us, what that matters is RNN is basically CNN plus memory. That's the general concept. And then became the issue that if I'm doing this kind of thing, right? I mean, I'm always computing new state from old state and the input, and of course I'm also computing an output. What are the limitations of these kind of systems and all? So firstly, one question which always comes is, can RNNs represent something that CNNs couldn't have? And there was a thesis defense in our department recently, or maybe it's upcoming. I saw the announcement of last week. And what she seems to have proven is that for a certain kind of RNN, whatever that RNN can do can be done by a CNN of twice the size. In other words, restating it, what this is saying is that the memory is limited. In other words, as we learn these things, the memory fades. Okay, as time progresses, then the state HT-1 is representing newer information well, information from way past not very good. And if that's the case, if let's say let's say it only represents information corresponding to inputs in the last 5 time steps. Let's say that's the case. Then that means a convolutional neural network of 5 time steps would do the trick. Going back to the video example, 5 frames would suffice. Okay. So there are some results suggesting rigorously, theoretically, that these things have an RNN with n neurons is similar to a CNN with 2n neurons under certain set of assumptions and all. Okay, so leaving that bit aside, I think it's an important thing, because one thing we have to recognize is that we can't represent things from far apart. So if you expect RNNs of the type we use to connect inputs which are occurring many samples apart, it would be hard for them to do. Okay, the memory, the context that they're sensitive to is relatively tiny. And there's some other results which indicate that it's like modern architectures have memory of like 1,000 tokens, 1,000 samples, which if you think in terms of a 30 frame per second video, then that's like 30 seconds. Okay, so there are limitations to these things. But otherwise, I mean, you can think of that what is happening is that at every time step, it's taking an input from the preceding, state from the preceding step, current input, and producing the next state and output. So this is a view which is unfolded in time. And when you train this thing, you have to now back propagate in time also, right? Because an output at any point at any time step, its error not only depends upon the input currently, but also inputs way in the past. So when they do back propagate, they have to kind of go back in time, and that introduces complications. Again, as a practitioner in the field, the tools do it for you, but if you were to hand compute the derivative of error with respect to a particular parameter value, you'll have to do it over multiple time steps. And that of course is impractical, but then what they do is they truncate it, okay, and which kind of makes sense, because I'm also separately making the point that these things have finite memory. So if they have finite memory, why go way back in the past? So all of that gets done. Then the next question is what happens inside it, in the sense that where it takes the state and the current input and produces the next state kind of output. And much of the work which has happened is really exploring different architectures for this green box, okay, what goes inside. And kind of things people are worried about is how are there ways in which I can remember things which are way in the past. So sometimes we organize these things hierarchically. So you'll have one layer, one RNN layer, which will handle sort of short time scale stuff, and then the next high level stuff will operate at a coarser time scale and coarser time scale. So Swapnil had a slide which he had called as temporal convolution neural network. It was kind of exploring the same idea. So are there ways in which I can detect things at multiple time scales? Because if you think about our activities, right, I mean, let's say I have an accelerometer, right? Clearly it's picking up things which are at the time scale of sampling rate, which is like, let's say, a kilohertz or 100 hertz. But then the way we work, there are rhythms, right? I mean, we take steps. So there are rhythms and steps, which may be, let's say, half a second, quarter of a second. But then there are rhythms in terms of our daily movement, right? I mean, we walk, sit, and all, right, at that level. Then there are even coarser level rhythms. So there are attempts to capture these things out there. This particular, the two particular ones you are seeing is, one is this long shot from memory. And I'm not going to details of it, but this is the one which the Swiss group had come up in 1990s. And it basically sought to have this notion of memory which is long term and memory which is short term. So here, if you see, the state actually has two components to it. There is a G-1 and then this H-1. And one of them is capturing kind of short time scale memory, and another is capturing long time scale memory. If if you kind of notice, the long time scale memory kind of just passes through with little additions and subtractions happening to it. Okay, but the short time scale memory is a lot more complex. Later, I think like 2010ish, 12ish, something like that, a group at Stanford / Google, I think, came up with this thing called gated recurrent unit, GRU, and much simpler. So that was a big claim to fame. But this was the one where they totally ignored the existence of LSTM, and that led to a lot of sort of nasty back and forth. But eventually they revised the paper and acknowledged network. So at this stage, this is the other RNN that exists. So these are the two common architectures, computationally simple, but this one has, LSTM has more powerful representation of time. So where does it leave us? If you have sensor data, we can certainly do multi-layer perceptron, and if at the very least, I would say you should certainly go after CNNs, because there is structural locality in time that most sensing phenomena have, so that kind of makes sense. You can also, instead of that, you can go to LSTM or GRUs, but generally people use LSTMs, partly because LSTM, while they are computationally more expensive, a lot of sensor data is one dimensional, so it's already, you have a big advantage over videos. So LSTM, so now what is happening is what typical way of using LSTM would be, we'll take a window, and then instead of computing features and all over it and then doing decision tree and all, so that window of time, I'm just going to feed the samples into LSTM, that window worth of samples, and then the LSTM will tell me for that window what the classification was. So I do a many to one or many to many, depending on the needs type thing. Okay, so that's LSTM. So I feed raw data and feed into LSTM and does the classification. Probably the most successful ones are which combine convolution and LSTM. So what we do now is we take our time series, we feed it through convolutional layers. I get now a time series of features, right? Those activation values, and then I feed those into an LSTM. So the LSTM, instead of operating over the raw samples, is now operating on vectors produced by the convolutional layers, and then it's seeing a sequence of those vectors, and that's what it's operating on. So these are called con LSTM, and generally speaking, for a lot of tasks like activity recognition and all, they are the highest performing things. That highest performing until some very recent stuff which is based around transformers and all, but so reasonable thing to go for. So what is happening there, right? I mean, in the convolutional days, we would do convolutional pooling followed by a dense layer. Now what we do with con LSTM, convolution pooling followed by an LSTM instead of this dense thing. And so this captures temporal stuff better, and generally yields better results. So even if I may be operating over a 1 second window, 5 second window, kind of this kind of architecture helps out. So if I roll back, let's say 4 or 5 years ago, these kind of architectures began to emerge and did pretty well for a variety of things like activity recognition, audio analysis, these kind of things. So let's see. Let's take our 5-minute break at this point, and then I'll continue. So 5 minutes.
So, which professor was it?
Achyuta
Is he in,
the physics one.
is he in
EC.
physics?
EC.
Okay.
EC.
Physical and wave electronics?
No. I don't know. He's probably signals and systems.
Signals and systems?
He's a computer vision person. Yeah, but his is not the only work. So if you Google for physics from neural networks, you would see that there's a lot of recent work.
Physics from neural networks.
Yeah. Neural network learning physics. Yeah, there's a lot of interesting activity in that space. Yeah.
Okay.
Any developments on your end, project-wise?
And then on Saturday, maybe we can discuss more.
Like if you were to say,
This is gonna be an interesting weekend, I'll say that. Both my projects for every semester, so.
I could try it out. Like I could, like because most of the time, the certain things between the time of the music is don't go over the vouchers. So I can bump it up the voucher and then drop that.
Want to talk or something?
Oh no.
Yeah,
just
sure. Okay.
the stress from
Well, we can probably get it all doing bare minimum.
So I've gotten some progress on like the question how long is
It's like,
okay.
so like, the problem is
I
like,
can probably do like a
I
PCA
can
or
get the
like
sensitivity, that's not just the
I guess you're right. I was just less.
I can go,
I can probably
like, I'm using, bring up function and says, like, the ESP, like, include library.
So guess you're right.
And if we go, like, steps back, and just, like, use your stuff correctly, and output it, put it that way, and look at, like, actually time, how long your transmission is. So, like, take it, read the time, like, the clock time or whatever, output, read it, and then re-output. So, saying that people find out how long it output can take longer than. Yeah. Two things. We have to be able to figure out connections.
It's good that we're closer to the end game, because the robotics project is quite complicated. Probably understand the capabilities of it. I wanna make sure I get that one down pat.
And doesn't sound like you hold on. But
Okay, I think we can restart. So let's look at couple of examples on how we might. So one is this whole area called human activity recognition. The word activity is deliberately vague out here, but usually people look for things like there's a person walking, standing, sitting, stuff like that. So kind of what the STM speaker had called as the base context. Okay, so that's kind of the intention. So very often, so you can imagine many ways of doing it. I mean, cameras, obviously, sound sensors, accelerometers, so kind of wearables like stuff from whatever wearables like this, or even from your smartphones. Okay, particularly if the smartphone is in your hand or pocket, you can make inferences. Not if it's sitting on the desk, obviously. Then also radar, that's another source of information. Like I said, sound. I mean, walking footsteps and all can do some stuff. What else have I seen? Yeah, they're probably these are the typical sensors. Okay, actually, it turns out also Wi-Fi signals can capture these things also, so it's kind of like a radar. So, okay, so but most typically when people talk about HAR, human activity recognition, they're really kind of usually talking about IMUs, inertial measurement units. So the standard approach in this thing is we take our time series, we create a sliding window of some form, and one of the questions is your window. So whenever you divide infinite time series or semi-infinite time series, typically, whenever you divide it into a window, two questions you have to ask: what is the length of the window, and what's the stride of the window? Okay, so very commonly the two are the same. So I create a length of a window, let's say 1 second, that's one window. Next window is when the preceding window ends. But by having a stride to be different than the length, you can have a smoother prediction possibly. So anyway, one has to consider those things. But then within that window, we do some map to some features, as we had talked earlier in the preceding earlier in this module, and then we do pattern classification over it. But with LSTM, your feature, well, in some cases, your feature, both with CNN and LSTM, your feature may be the same as the measurement. It's rarer, as Swapnil also mentioned, but certainly a lot of people do it, and there is a lot of push towards that for a variety of reasons. So the ML pipeline of HAR then typically looks like you collect the label data, you do some data pre-processing, you train the neural network model, and then kind of you deploy it. And this is what tools like Edge Impulse that Swapnil also mentioned kind of take care of it very well. So some of the decisions that one has to make: should one work with raw data? Should one work with features, windows? If windows, what size windows? All kind of things one has to worry about. So, like I said, traditional practice was take window, usually windows which are non-overlapping, do some features, do decision tree or even neural network. I think now not at all uncommon that we just feed this raw data directly to a neural network, and part of the reason is that particularly if you are using convolutional LSTM or CNN, your convolutional layers essentially learned features. When you train a CNN, remember we had those filters are effectively learning features. So the whole reason for the switch to neural networks is that we avoid feature engineering. Rather, we learn the features which are good from the data. So, so that's kind of the rationale. There is one little gotcha in that, which is in order for us to be able to apply convolutional layers, our data has to be regularly sampled, and that is often not true when data are missing. Some samples are missing. So one of the advantages of classical feature engineering is that I can pick features which are more robust to missing samples and stuff like that. Okay, but if you're using a convolutional thing, then you have to supply all the pixels in the image, or do something about it. One strategy, if you have missing samples, is the following: that let's say I have an image or whatever time series for a window, and let's say I have a time series of 10 samples. Okay, then it's possible, let's say sample number 5 is missing. So I have no value available for it. So how can I handle with a convolutional architecture? So one common strategy is that not only do we give the sample time series, but I give a secondary time series, which is a mask time series, and it's just one bit per sample. So wherever the true value is present, I'll put a 1. Wherever the true value is missing, I'll put a 0. In context of images, you can think of as RGB and then a mask. So there's a depth of 4. So I'm feeding RGB and some pixels may be missing because maybe network packet loss or something, and then the mask image will tell us that the pixel is missing. And then during training, what you do is you deliberately subject it to lots of examples with missing samples of different times along with the corresponding mask. So that's one way we can handle things. Okay. So in any case, that's kind of a high level approach. I think we have done these kind of things. I'm going to skip window size and stride I have discussed. So in terms of the performance, this is just kind of an example. So this is for Thar, and what you see is multi-layer perceptron. Remember, multi-layer perceptron, everything is connected to everything. You might think that, hey, this should do better, but the problem is for the same amount of data, if you have more parameters, then you can do worse because you don't have enough data. CNN, LSTM, convolution and STM. And in this case, you see convolution and STM is doing the best. A lot of these things are a little bit hard to also, I mean, this is taken from one particular presentation, so it's also not very clear how much of like architecture search they did they do network architecture search to optimize the number of neurons, and also some of these things you have to take with a little bit of grain of salt, because it's not that these numbers correspond to the best representation of convolution LSTM. And then the other question you have to ask is, what is it that they are keeping constant? A fair comparison, for example, arguably would be that I would say for the same number of parameters overall, if I were to pick these 4 architectures, which one does the best? Or I could say for same amount of training time, or given with the same amount of data. You have to keep some, you have to normalize something, and usually these kind of works don't do it. But anyways, usually what we have seen is in recent years, without going to transformer type architectures, the best results have been from convolution LSTM. So they identify the right features, they discover the features, and then they also exploit the temporal thing. Okay, same kind of things for acoustic. So standard approaches with acoustic have relied on more classical signal processing inspired stuff. So we have seen these things. HMM was very common, and Gaussian mixture modeling, which again we kind of saw. These kind of things have been very common in speech. So if you do the speech courses and all, usually they would talk about this. But in recent times, again, deep learning type approaches emerged. So there was a famous paper, Deep Ear, I think it's out of Google, which again applied convolutional neural networks and produced kind of much better results. So if you follow again the past, whatever, let's say 6-7 years worth, there's a big shift happened towards neural networks for acoustic also, and acoustic event detection and all sort of acoustic tasks. At this point, neural networks do much better. Again, the caveat with all of this is amount of data. If you have very little data, then hard to train a meaningful model. So that's deep ear performance, and I think domain after domain that kind of generally holds true. Now, having said that, there are issues one has to bear in mind. Neural networks, of even the small ones which you would need for this kind of thing, I mean, they're not as big as language models and computer vision models. They are nevertheless far more power hungry than a little decision tree or a little linear regressor or a little even support vector machine. So if you notice, the ST Microelectronics, their approach was for on-chip inferencing, is that they had a bank of features. So every window they will compute those features, and then you do a decision tree on it. And I recall kind of they were saying they're able to do these things in like microamps. Okay, So that's the big win that they have, but it comes at a cost. So again, during Dr. Chaudhary's presentation, you might recall I had asked the question, what is the loss in accuracy? And he kind of didn't answer that question, but apparently there's a reasonable loss of accuracy which happens between decision tree versus neural network models of like, let's say 5 to 10%, which is quite a bit. So probably the best way of using these things is that use a simple neural network on sensor to make a quick determination. If you have a very high confidence in your result, you can stop there. If not, then run the neural network either right on that chip or ship the data or ship the features to next layer up to a Raspberry Pi or even to the cloud, and then have things being done. There is also a class of neural networks which are called early exit neural networks. And what happens there is that you have the CNN layers, and then you have different complexities of think of it like this. It's a neural network which is very deep. You could go all the way and get a very high quality result, but you could also stop somewhere in the middle and get a poorer quality result. So it should remind you a little bit of the IROS task or approximate computing that we had discussed earlier. Okay, so you kind of start processing, let's say you do a few CNN layers and then you do a fully connected layer, you get a quick and dirty determination and some way of getting a sense of confidence in that result. And if you are highly confident with that simple result, you can stop there. Otherwise, you apply more layers and sort of do some more processing. Again, do the same process. So they're called early exit neural networks, and a lot of people in sensing kind of try to exploit that. That try early. If you have a high confidence result, stop. If not, do some more processing, then try again. Very crucial for those approaches to succeed is to have a notion of how confident you are, as I was referring, right? So when a neural network produces the results, it should also tell you how confident it is about that result. And this is where one thing which I forgot to mention, let me go back a lot of slides, I think. Let's see. Yeah, I don't have a slide on that. Yeah, okay. Let me hand wave my way through it a little bit. So ignore everything before the final two layers. So on the output, so let's say this is something which gives me a choice of 4 categories. Let's say it says whether it's whatever, car, scooter, bicycle, truck. Okay. So this is what would be referred to as a multi-class classifier, and what it would output is at this point probabilities that it thinks for the different classes. Okay, so again, let's say, yeah, so car, scooter, bicycle, truck. So it will output 4 probabilities. So that's what we want. That's how these networks are designed to do. And what they do is they use a function called softmax in order to do it. So what is softmax? So the preceding layers here, so let's say there is a softmax layer here which will do that. The preceding layers are giving us 4 numbers, but those numbers may not represent probabilities. But they do have the thing that if they are high values, then I'm more confident that more likely it is that class. If there's a low value, less likely. So softmax is a function which takes real numbers, k real numbers, and converts it into k numbers which satisfy the rules of probability. As in, they'll add up to 1, and they will have the same relationship, as in higher the value of the input, higher the value on the output. So all neural networks have, well, I shouldn't say all, but almost everything that you'll encounter, the very final layer would be that softmax layer. It converts a vector of real number values into a vector of equivalent probability. So if you see some of my later diagrams had that softmax listed out there, like for example, softmax, and that's why we have the probability, right? So softmax converts the output of let's say a dense connected layer into probability vectors. So oftentimes people use probabilities that are output by softmax as a degree of confidence. So like let's say I had 4 categories and one of them said 0.95 it is a car, and then the 0.05 is distributed among others. Then I can take that, oh, it's a strong result, so I can go for it. On the other hand, if something says it's 0.55 is a car and 0.49 it's a scooter and so on and so forth, then I would be more ambivalent about it. So that's one way of doing it, except that probabilities are not quite the same thing as confidence. It turns out that neural networks often can give you very confident results, like 0.95 it is a car, but they're wrong, totally wrong. So this whole notion of confidently wrong is something that also causes a lot of trouble in neural networks, and there are ways to handle it. So there's a lot of work on like different ways of representing uncertainty. Part of the challenge, as you can see with the way I framed it, right, was 4 categories, is I didn't make any allowance for I don't know or I am confused. So there are 2 ways, like if think about yourself, right? I mean, let's say I ask you to classify some fruit I show you. There are a couple of ways we run into problem. One is, it kind of looks like an apple, but it could also be a guava. Okay, I don't know, it looks a little bit of both. It's sitting at that boundary between 2 fruits. So that's ambiguity. So oftentimes we face that. And the other one is I show you a fruit which you have never seen before, maybe from some tropical country. I don't know what it is, and that also we need to be able to express. So softmax kind of falls apart under those settings, ambiguity and particularly the notion of I don't know. So there are various ways of, again, people try to handle these things, but just want to throw that out that it's also an important consideration that we should be able to reason about the uncertainty. Am I seeing something novel? That's one issue, and am I seeing something which is very close to the decision boundary and therefore I can't make up my mind whether it's A or B. So right, so I don't know, and the ambiguity. Both of these things one has to be able to do it. Softmax probably does the ambiguity part okay, in the sense that you would expect probabilities to be similar, but I don't know part, it can be very off on that. Okay, so that's on the neural network side. Let's see, how are we doing on time? Okay, so okay, so change of gears. So we have examined how sensing is done, and we kind of I think between material I presented and material Swapnil presented, hopefully you get a sense of like what some of the reasonably current techniques are. We haven't covered some of the latest architectures that have emerged, transformers for example. Part of the reason is they're mostly being applied still to language and vision and less so to sensor data, but there are papers which are applying them there. The conference I was in, because of it, I couldn't give the Tuesday lecture. I saw several papers around that. Okay. The other thing is, I mentioned that neural networks cannot handle data where samples are missing and all, right? I mean, so again, there is stuff for handling that, but they're kind of not very mature. Loosely speaking, the idea is instead of giving you time samples, I give you a time sample, a value and a timestamp, and then the networks are designed to operate on a set of values where each value is a tuple, a value and a timestamp. So that way I can handle irregular data. Again, not very mature. So what we have described to you is pretty close to what you will find in practice. So now change of gears. One thing which embedded systems have rely extremely heavily on is the notion of time. And the other thing they rely very heavily, perhaps less heavily, but nevertheless very heavily, is notion of location or location of space. And these two are kind of, along with energy, are kind of the building blocks of any embedded systems. So we already saw how to manage CPU or resources, but how to have a good notion of time, how to have a good notion of location, and how to manage energy are kind of three other pieces that people worry about. So this module and the next one is going to examine the time part a little bit more, because it's as core to being foundational as it exists. So let's talk about it. So we need to, I guess a lot of things we do in computing and broadly in our life rely on some notion of time. And it's been quite foundational that historically there have been some significant competitions and major prizes and all to create systems that could accurately determine time or accurately on clocks. And location is very closely tied with time, so oftentimes they have been because of location. So back in 15th century, when naval exploration really became very dominant, particularly by the European powers, for a ship to figure out in the ocean where it is was supremely important. Otherwise, you will end up in America instead of India. So a lot of now, if you think about how latitude can be measured relatively easily by measuring the angle above the horizon of a particular, let's say the North Star or whatever, right? So that's easy. But longitude required, at least the simplest way you can think of doing longitude requires knowing time. And why is that? Anyone? How can time tell you longitude?
Sunrise, sunset.
Yeah, or with noon, so you can look at the peak sun place and then how at what time it was happening. Okay, so you could. Okay, so there was a competition that the British government ran, and which was in today's term $2 million. So it was a pretty significant prize, as you might imagine, which was to create a system which could localize the time, and in order to do that, it needed to keep time to 3 seconds per day, and then it was not some highly trained scientist and all. It was some more like a vocational person who kind of won this thing. Anyways, in London there is a museum at the Greenwich Line where they go through the history of these things and kind of the clocks and all that were developed and all. So I guess the point is long history continues to this date. Your missiles depend very heavily, cellular system, GPS, right? They all depend upon atomic clocks and very precise timekeeping. And also timekeeping has been just precise timekeeping has been with us. Communication, energy management, all of these things, even our electrical grid, they all depend upon kind of precise timing and clocking. So there's a long history from way back from sort of thousands of BC all the way to kind of the most modern things. I think the most interesting development in recent times have been atomic clocks, which are super tiny. So they're called chip scale atomic clocks. It's a program which was started a couple of decades ago, but now you can buy an atomic clock which is a chip sized thing with around $1,000, $1,500 Yeah, they're not as accurate as the big atomic clocks, but good enough. And then, of course, if you have a GPS receiver or if you have a phone with a GPS receiver, then by consulting the GPS satellites, you can effectively set time close to atomic clock accuracies there. So, so probably, like for me, the most accurate clock I have with me is my Apple Watch. Okay, it's very, very accurate because it again syncs with the GPS even more so than the iPhone, because the phones often rely on the internet time protocol. So big advances have happened that today you can safely say that I can measure time to a few tenths of nanosecond accuracy relatively easily from consumer devices anywhere on the planet. Okay, and then certain applications you need to go even more accurate. So like physicists and all who are doing subatomic type experiments and all, they of course need to go into picoseconds and femtoseconds. And when I say accuracy, there are many different notions you can imagine, right? I mean, one is, can I measure a time interval accurately, right? I mean, for example, event 1 happened, event 2 happened. I want to measure the time gap between the two. Can I measure that very accurately? Another one is, what time is it now? Now you should ask, what time is it now relative to what? So there has to be some coordinate system. So with respect to which, so humanity has a coordinate system for time. It's called UTC. So often you see time written as UTC, right? Universal Coordinated Time. But yes, the UTC is the French version of it. So yeah, okay. The UTC time is kind of an interesting one. You cannot tell what time it is right now in UTC, because the way UTC works is, at the end of a 24-hour period, they go back in time and then describe what the corrections were. So it's an average of, I think, 24 or 30 atomic clocks all over the world, and then from that they kind of calculate it. So it's a more complicated thing, but we have a pretty good notion of time. When time goes wrong, as in if somehow your system has a wrong notion of time, all type of hell breaks loose, and it has happened. Okay, and in particular because we often rely on GPS satellites to maintain time, so anything that attacks the signal from the GPS satellites can cause problems, for example. Okay, so that's the high level bit. For our purposes, both what time it is matters, because then we can coordinate with others, right? Let's say two embedded systems want to jointly do a task, they need to have a shared notion of time. Ability to measure interval of time is important, because that's how we set frequency. If I tell you that I'm sending you data at 1 megabit per second, then I'm going to send bits which are 1 microsecond long, but your notion of 1 microsecond and my notion of 1 microsecond need to be the same. Often many settings, time will translate into physical variables. If I'm observing two events and based on the time I will say what the speed of the object was, then if I get time wrong, then the speed is wrong. Time can also matter for ordering of events, right? Which sensor saw something first. So I can go on and on, but clearly good timing is important. So in terms of how time second is defined, I'm sure when you took physics and all, they talk about how for most of our fundamental things like what's a kilogram and what's a meter and all, there are sort of ways of defining it. So likewise for second, it's a particular number of transitions of cesium atom, and so cesium atomic clocks by definition are kind of the standard, so everything else is defined with reference to those. Yeah.
Why that particular number?
Because why that particular number? Because I think all of these things, when they were decided, speed of light had a big role to play, and some things like meter were already in existence in kilograms, or like there were specific masses which corresponded to a kilogram of mass, and there was something specific which was a meter in length. So they kind of then picked things around that, and then once these things became fixed, then the other stuff got removed. So like basically we have been moving away from having physical standards to standards which are fundamental there. This should, by the way, kind of one thing to keep in mind out here is that it's possible that let's say there were two oscillators. Cesium atom in this case is nothing but an oscillator, right? So if I had two oscillators and which right now had the same frequency, let's say there was cesium atom and atom X, okay, and let's say cesium atom's frequency was the same as that of atom X, but let's say for whatever reason, some unknown physics, atom X versus cesium atom frequencies are no longer aligned, right? But with this view we are saying that we don't know which one changed, because that notion doesn't make sense. We are just saying that a second is exactly this very thing. Okay, so the other entity changed. Okay, so most accurate, I think this number is clearly, it's probably not very accurate. Clocks keep improving a lot. So a lot of sort of improvements in atomic clock technologies and all keep happening. NIST, which is a federal government agency, National Institutes of Standard and Technology, they have a big setup in Boulder, Colorado, which is all devoted to keeping time and all. Okay, so basically there are things are in safe hand. Part of it is a lot of its stuff has immense military use, so it's kind of taken with appropriate seriousness. UTC, as I mentioned, is a weighted sum of, okay, I was wrong with that, 300 atomic clocks, okay. And basically when you hear about like these things like leap seconds and stuff like that, right, I mean occasionally at the end of the year they'll say, oh, there will be a leap second added this year, and also they do corrections. There is a push against it also. Google in particular has been pushing doing away with leap seconds, because that leap second where they add or subtract a second at the end of the year creates havoc with the cloud computing services and all. So Google has been doing something around, instead of a second being added at the midnight of December 31st, they kind of smear the leap second over some time period so that it's a more graceful thing. So lots and lots of stuff. Very interestingly, there's a professor here in CS, Paul Eggert. He has been kind of the unofficial czar for maintaining internet's time zone thing. So whenever your computer correctly calculates time zone translation between different countries and like switching of daylight saving time, there are all sort of complicated rules and regulations and all, and something has to interpret them, and right, and then parliaments change the laws and all. So like all the time, right, there is a debate in this country into whether we should have daylight saving time or not, or should we always have standard time, things like that. All of that has to be encoded in rules and all, and he maintains that. So it's pretty cool that sort of UCLA has a big role in that. UTC is this weighted average, but of course the average can only be done at the end of the day, at the end of some time period. So in some senses UTC is a retrospective time, okay, kind of looks back and provides the correction factors. So time, because it has been so foundational, people have thought about it like, firstly, what is time, right? And even in physics and all, I mean Einstein's experiments with space and time are super famous, but in distributed computing, time is super important. So one of the things in distributed computing, which I'm just going to say that and stop. One of the things in distributed computing always has been this notion of consensus or agreement. Bunch of computers agreeing upon a common thing. And there are, so like for example, let's say your checking account, a transaction hit for the withdrawal and a transaction hit for deduction, and they happen in two different places on the planet. Which one happened first? Well, we need to agree commonly on that. So that all these elaborate protocols and all for distributed coordination among devices, okay, among sensors or robots or whatnot. And if everyone had precise timing, like really, really, truly precise timing, distributed computing would be very easy, because all we have to do is to timestamp and consult that, right? I mean, just imagine if every computer, every sensor had a super accurate, whatever, 10 to power minus zillion accurate thing, then coordination problem becomes super simple. We can just go with that timestamp. But of course, we don't have that. So that leads to coming up with ways to solve various timing related problems, and we will talk about that on Tuesday.